All right, the goal of this video is to talk about mechanical waves, and we'll talk about these three things: the medium, the disturbance causing the wave, and the mechanism that allows the wave to transmit. Give me just a second. Well, let's just start right there. Medium is the material in which the wave travels. So a sound wave travels through the air, or it could travel through water or steel. You could have a water wave, and it's propagating through water. So there's different types of waves. Well, they all have a medium if they are a mechanical wave. Later, we'll learn about electromagnetic waves, which do not require a medium. They can travel through a vacuum. But these are mechanical waves. We're going to assume mechanical waves need a medium. It could be air, it could be water, it could be a string. Okay, disturbance. I will say it like this. Some disruption or wiggling which starts, the energy traveling. So in a wave, we're going to have energy traveling down through the water or through the air or down the length of a string. So there has to be some disruption. Something has to wiggle somewhere, which starts that energy traveling down the medium. And then the mechanism. So there's got to be some kind of coupling, some kind of connection. So we could say, perhaps you want to say, transmit energy. There's got to be some kind of mechanism which allows one part of the medium to talk to the next part. So it could be one part of the string connects to the next part of the string, and tension is the mechanism that allows it. Or we could have intermolecular forces, right? Maybe a sound wave in the air. There's air molecules literally smashing into each other. Okay. Or surface tension for a water wave, perhaps. All right. And let's go ahead and look at some physical examples of this. All right, give me just a second here. Oops. Back that up a little bit. All right, that's pretty close. Okay. So you can see we have, I have some long metal rods here. They're connected. Let me get around the front side here. All along this long axis, there's a wire essentially running. And then to connect these really long sections, you may notice I put some rubber bands here and here. That's just to connect this section to this one, and these rubber bands connect this section to that one. Now, without further ado, I'm just going to wiggle this thing, and we'll talk about the mechanism, the medium, and the disturbance in just a minute. But so you probably want to watch quickly. I don't know if you need to slow this down, but you can rewind it and watch it a couple of times. The first 5 pulses are going to come out pretty quickly, and then what's going to happen is when they reach this other end, the waves are going to start to reflect. It'll get more complicated. Let's worry about the reflections later. Try to just watch what happens as I wiggle this a few times and let these pulses go back and forth. I'm going to run that one more time. Flatten it out. Try it one more time. Flatten one more. Let me go a little bit slower here. All right, so there you can see what is called a transverse wave. In this case, I hope you noticed the wave is traveling, the wave energy is traveling this way, right? Energy propagates down this way, the wave propagates this direction. Whereas these individual rods are moving up and down. So the rods are not moving from one end to the other, but the energy is moving. So this is why we did oscillations first. In fact, we see that individual rods are oscillating up and down. The velocity of one element of the medium oscillates up and down while the wave is traveling left or right. So this is a transverse wave. We see the energy propagates in a direction perpendicular to the oscillation of an individual element of the medium. What? The rods oscillate up and down, but the energy travels left, right. Transverse wave. Waves that have that type of property are called transverse waves. All right, let's go to an example of a longitudinal wave. Actually, let's do this first. Let's go up to the whiteboard. Let's see if we can figure this out. If you want to pause the video really quick, you can. But try to fill in this chart for we just did the transverse wave. So think about what is the medium, the disturbance, and the mechanism. Go ahead and hit pause if you want. I'm going to go ahead and do it right now. Okay, the medium were the rods. I'll say running into and out of the page. So those were the rods that were going this way, not the long rod that was running along the length of the wave. The disturbance, that's me. I'm disturbing the medium. Okay, so I was wiggling the apparatus up and down. What was the mechanism? What was allowing this? That torsion rod was connecting so it's a little bit confusing because we had a long torsion rod and then we had the transverse rods. Okay, so in this case, basically the wire that was running, maybe we could call this the torsion wire just to speak a little bit more clearly about it. So the wire that was running the entire length was connecting these rods, and that allowed these rods, the tension in that torsion wire it would exert torques on the rod and cause the other rods to oscillate, right? So when one part of the medium went up, there would be some tension in this torsion rod, and that would cause the next one to twist. So this is the mechanism that's causing the energy to propagate. All right, so now let's go to this one. Come on. Give me just a second. All right, so this is an example of a longitudinal wave. If I could do this one. So again, I don't know if you could see, but there are some springs here and here. There are these vertical rods, and notice what happens. In this case, the wave energy, if I just flick this once, the wave energy traveled this way. Obviously, it's reflecting backwards at the end. But if I give it an initial pulse, every time I give it an initial pulse, the wave energy travels this way. But notice that the end of the rod is also displaced along the same direction. Longitudinal, if the element of the medium, the vertical rod, is displaced in the same direction as wave travels. Let me say that another way. Rod wiggles left, right. Wave energy travels left, right. Longitudinal wave. Let's go to the board. Whoa. Come on. Whoops, wrong board. Here we go. Let me get this out of here so I don't forget. All right. So in this case, if you want to pause the video, you can think about what this was. I'm going to go ahead and start writing them in. What was the mechanism connecting them? The tension in the springs was the mechanism that was allowing the energy to propagate from one rod to the next rod. All right. So some key differences here that I might mention really quick. In a wave, the energy travels from point A to point B. All right. So for a wave, the energy is traveling from one place to another. In an oscillation, like a pendulum going back and forth, there's kinetic energy, there's potential energy, but notice this pendulum is staying in place on average. So the energy is not going anywhere. It's right here where I'm at in this pendulum. Obviously, you could put a pendulum on a car. That would be a different problem. That's not what we're talking about. There's some focus issues there. Let's get this. Come on. All right, there we go. All right, so waves are different than oscillations in this key way. In a wave, the energy is going to travel from some spot to another spot. In an oscillation, it stays put on average. Okay, next up, let's go to board 2 here. Come on. Today. There we go. All right, so you may hear some physics instructor somewhere say the wave equation. This can be a little bit tricky because we're going to see lots of different equations that relate to waves. We might see the equation for the vertical position of a wave pulse. We might see the equation for a sinusoidal wave pulse, like a sine wave or something, right? We'll have pressure waves, we'll have displacement waves. But when a physics teacher says the wave equation or the wave equation, usually they mean this equation right here. Okay, so and in particular, I'm using a transverse wave. So this is the one where it was what you flick the wave pulse and it travels this, not this one. Let's get that out of here. It was the wave pulse, you flick it and it travels down the set of rods. Okay, these are partial derivatives. If you don't know what those are, you can look that up separately. They're actually easier than total derivatives. It just means anything in this function y, set it to a constant except for x, and then take the derivative. Similarly, this is a partial derivative with respect to time squared. And so you set everything in the equation for y to a constant except for time, and then take the derivative. So let's look at this. Here is a picture in time, like if you snapped a photo of the wave pulse, maybe it looks like this. It's traveling down here, and so some of the rods are up in the air, some are not. And so this would be a shape of the wave pulse at time t. That's what this function y means. Y is not the wave equation. The wave equation is this weird differential equation. Y is an equation for the shape of the wave pulse at some time t. Think about it. If you tell me the x value and you tell me what time it is, I can tell you how high up in the air any one rod might have been. So that's what this is really talking about, the shape. Solutions to the wave equations are the shape functions that I just talked about. So the wave equation is this weird differential equation. Solutions to the wave equation take this form. And maybe I'll emphasize this symbol here in blue. V is called wave speed. In a lot of books, you may actually see that written as the letter C, and we will use that sometimes too, especially for light waves. We say C is the speed of light in a vacuum. Sometimes you'll see C is the speed of sound in some books. Okay, but in general, we're going to call V wave speed. So if you want to have a legit solution to this differential equation, it must take on this form. The vertical position of the rod at position X and time t must take the form Y is a function of X minus VT. All right, if you have sinusoidal waves, it turns out omega is our same friend angular frequency. K is no longer spring constant. It's called wave number. It will relate to something called the wavelength. Whoops. It's 2 pi over the wavelength. And we will discuss this in greater detail in another video. Now, it turns out if you have a sinusoidal wave, you can also write it, you'll see this in a lot of textbooks like this. These waves can take on the form kx minus omega t. And I guess, strictly speaking, it could be plus or minus. All right. Now, in this case, let me give you an example. Here is a crazy example. If you give a quick flick to there and you make one pulse, we could make what's called a Gaussian wave pulse. It looks like this equation, right? Now, if you're wondering, could I factor out a k here? Yes, I could. I would get e to the negative k times the quantity, what would it be? X minus omega over k times t, and then there would be this a, which is called the amplitude. More on this in another video, but we'll revisit this soon. But I just wanted to point out kx minus omega t does really take the same shape as x plus or minus vt. So what does the plus and minus mean? Plus actually is moving left. Oops, and I'll say x plus vt would be moving left. You could have a wave in the y direction, y plus vt, that would be moving up. And then x minus vt moves right. So that's a little bit confusing here. The minus sign is associated with moving to the right. The plus sign is associated with moving to the left. So that's what the plus or minus means in this equation. All right, so we've seen examples of longitudinal waves. We've seen examples of transverse waves. And this thing is called the wave equation. If you're curious, on page 29 in volume 5 of the workbook, I derived this equation from for a wave on a string, and we talk about tension and how all that propagates through to get this result. Y is not the wave equation. That's the shape of your wave pulse, or the shape of your wave, or right, the shape of the disturbance that's propagating through. And finally, energy is what's traveling in a wave from point A to point B. The individual elements of the medium, on average, oscillate and stay put. It's called